And just a while ago, Lisa Long played with this to see the rainbow coming out. Here. It's not always, well, now you start to see a little bit rainbow, but if you get closer to see it on this screen. So, yeah, over here. Not so visible, but if we have another dispersion, you see a little bit. Blue light is sort of getting larger angle, and green light getting smaller angle. And so this means that the dispersion can separate this the light. Dispersion of the material can separate the light. And same thing, this point is a function of the wavelength. So this becomes a very powerful instrument. Quite often that when we do applications, we need to understand the dispersion of a material. How do we measure it? How do we measure it? Well, basically, we measure this minimal deviation angle. Okay, because minimal deviation angle is a function of wavelength. So this. I need to be consistent, so let me change this to alpha. You can also change this in your handout. This is alpha. All right. So in fact, this phenomenon give a quite useful instrument for measuring the refractive index of a material versus wavelength. Okay. Now today, you can still buy this instrument in the market. If you want to figure out the refractive index of some material versus wavelength, then you build the instrument exactly the same concept, and then measure the refractive index versus this minimal deviation angle. This alpha is the apex angle of this prism. And then I leave a question in the handout to tell you that not all the apex angle will give you a minimal deviation angle, and I ask you why. Okay, if you play with that prism, well, just a while ago we played with the prism, but then we choose the apex angle to be this 45 degree, right? But now if you choose the apex angle to be 90 degree, you will never see the minimal deviation angle. And then I ask why in the handout, and then you please figure out why. Okay. So you can struggle by yourself a little bit by using the 90 degree apex angle to find the minimal deviation angle, and then you'll fail. Okay. So not all the apex angle will give you this minimal deviation angle, and but this becomes a quite sensitive experimental skill to determine the refractive index of a material as a function of wavelengths, because for different wavelengths, this point is going to be along different direction. So this is one application. Okay. By looking into the minimal deviation angle to find out the dispersion of the material. Another second application is what we call harmonic separator. Okay, what is a harmonic separator? Well, I like to study physics, but I'm also very practical. So I look into a lot of applications. Well, something is called harmonic separator. You know how the green light, the green laser is generated. Okay, the green laser over there in your hand is consists of a laser crystal, and then you have some light to pump it, and then this laser crystal will produce an infrared light at 1064 nanometer. you cannot see it because this is infrared light. And then you have a second harmonic generator right here to produce 532 nanometer. Right, that is 1064 nanometer divided by 2. So the frequency double in this crystal. We call this harmonic generator. Well, the conversion efficiency is not 100%. So at the output, you have this 1064 nanometer and 532 nanometer at the same time. How do you separate these two? If you just want this green light, okay, if you just want this green light for your application, how do you separate these two components? Well, people invented this parabolic prism. If you have multiple wavelengths of light going into this, at an exit, 90-degree exit, at exactly 90-degree direction for your application, you only have one color going along this direction. Okay. If you need another color, then you rotate this a little bit to allow another color to go down at 90 degrees. And we call this the harmonic separator. And the underlying basically the principle, the functioning principle of this is based on this. Well, let's decompose this parabolic prism into 3 pieces. 1, 2, 3. This is right angle prism, and this is another right angle prism, and then finally you have third right angle prism. The arrangement basically is to have this 90-degree band in the structure. Okay, so think about that when you have a refraction of the light going into this prism. But this is the normal instance, so just go straight here, and then you have 90-degree band in the prism, just like if I do this. If I do this, I can have a 90-degree bending of the light if I want to have the laser go in this direction and bend it 90 degrees along that direction. Basically, I just send my laser along this direction. You see along my 90-degree direction, I can bend the light 90 degrees, right? And same thing right here. You have 90-degree bending of the light. So this prism basically is just for a total internal refraction for 90-degree bending. And then you follow this line to the second edge of the prism. This is the first edge of the prism. This is the second edge of the prism. If you look at this construction, this is the first edge of the prism. This is the second edge of the prism. And between these two edges, there's an apex angle. So you have a minimum deviation angle. Same thing for this one. You have the first edge of the prism. You have the second edge of the prism. And then this line and this line, between these two lights, you have a minimum deviation angle. That is close to 90 degrees. Okay. If you have this, it's not possible to move this point to 90 degrees. Okay. But if you want to have a 90-degree bending for your application, then you add one more prism here to have 90-degree bending. The minimum deviation angle now is 90 degrees. So this is how you use it for your application. Is there any question about this? Let's come back here. You want to operate at this point, but this point will never come to 90 degrees. Okay, and this is inconvenient, right? With some arbitrary angle coming in and going out. Well, then let's add something here to make it bend 90 degrees. Well, the way to add it is to add this piece of prism to have a total internal refraction with a 90-degree bending. And then this serves as a second prism to get this minimum deviation angle. And this is called the Perindoka prism. So if you have multiple color light going in, then by rotating this a little bit, you will be able to separate the different colors of light. So this is the very useful prism. Quite often that is installed to a laser source generating different colors. All right, and there are different kinds of prisms, and taking advantage of the total internal refraction. Remember, you have an internal refraction inside some glass that gives you total internal refraction. So, but then if you take the images, you need to be careful that sometimes the direction of the image will change. For example, if you have such a prism, and then you take the image through, for example, if you have an object here, and then you take the image here, then left and right and up and down will change. Okay. For example, for this one, you have the image. You have some object like this, but then if you take the image here, this part is going to be pointed downward, and left and right are still symmetric, but up and down will be anti-symmetric. Okay. Same thing happened to this. Left and right is symmetric, but then up and down is already the flip, 180 degrees. So if you use prisms to take the image, then you need to be careful that the symmetry of your object in the image could be different. All right, so this is the more like prism because it's so popular. So I spend a little bit of time on this, and I hope that you have enough fun to see the real phenomenon. All right, optic fiber. Optic fiber. In the handout, we talk about this in chapter 0, but I wait until now to show you. Well, an optic fiber take advantage of the total internal refraction inside the fiber structure. So in general, you have two parts in your fiber. One is the core, the other is cladding. The refracting index of the core is slightly larger than the refracting index of the cladding. Okay, and then if you have an internal refraction, then there's a critical angle allow you to trap all the energy of the radiation inside. And this is the functioning principle of optic fiber, and it's a Nobel Prize. Surprisingly simple. So then it changed the whole world because you can talk over very, very long distance by using a piece of optical signals going through an optical fiber. And then there's a opening angle, just like the way we define the entrance pupil and exit pupil. There's a cone of the light ray can enter this and trap inside this optical fiber, and then you can go through the calculation to find out the opening angle, and we call this numerical aperture. Okay, the derivation is given in the handout. Okay, so this is the optical fiber, and several of you have seen I play this when I talk about the electromagnetic wave. And some of you haven't seen it, but you could have seen this when you were a little kid. So this is usually I want to show you. So this is the jasmine flower when you were little kids. You saw this before. This is a plastic fiber, and then you see the light coming out like this. And then in the supermarket, you can buy this with the LED, different colors of the LED underneath. and so it becomes a Christmas decoration. And when you see this light coming out here, you don't quite see anything here. So this means that the light does not go out through the boundary of the fiber. It just come out from the end of the fiber. So the energy is guided inside. Okay, it does not go out. So this is the sort of toy that, well, everybody saw this before when you were a little kid, right? And then this beautiful thing, and then people call this jasmine flower. Yeah, it's quite fascinating. If I have different color, well, previously at my home, I have one like this with the LED, white light LED here, and then we have optical filters rotating, selecting different colors coming from the white light LED, and then the colors coming out from this jasmine flower just change. And that was something that my daughters really love. Anyway, so this is optical fiber. So more or less, you see the optical phenomena we introduced, and I hope that you can remember it, and hope that it's more fun. All right, optical fibers have been very, very important for communications, and so today, if somebody cut the on the ocean cable, then we cannot talk, we cannot communicate. And the undersea cable consists of a lot of optic fibers. Okay, but we could have different kinds of fibers. Previously on this page, we have step index fiber because the refractive index change in step like this. The core refractive index is higher, and the cladding refractive index is reduced a little bit, okay, and we call this a step index fiber. But quite often, to reduce the dispersion of the fiber, you can have this kind of graded index fiber. It's a soft aperture for the core material, okay, and then the dispersion, especially when we say modal dispersion of the fiber, is going to be reduced. Not quite the chromatic dispersion. So now we touched upon some concept of different kinds of dispersion. Okay, one dispersion is this. You already understood. This is material dispersion, because the dipole will oscillate with different strengths at different frequencies. So we have material dispersion. But then dispersion, if we understood dispersion as the speed of the light propagating at different value for different wavelengths, then we could also understood it as signal propagation at different speeds for different kind of signal modes. Well, think about there's a waveguide. The light can do this at some instant angle, right? If I send a signal inside some waveguide or optic fiber, it can propagate with some certain angle. But this is the signal coming. But this is the signal associated with this. Let me call this Y angle. Sigma I, Y color angle. But this signal can also propagate with this. This will have an angle of sigma I. This can also carry information. This will carry some information as well. Agreed? But the velocity of this light and this light reaching, well, the time for this signal and for this signal to reach the end of fiber will be different, right? Because this Y ray is going to have more bouncing. The angle is smaller. Do you agree? Okay. So this is one kind of mode inside this waveguide. This is another kind of mode in this waveguide. But turned out that the time for the two signals to propagate to the end of the fiber will be different. So this means effectively, this guy is propagating slower. This guy is propagating faster. You can agree, right? Because this has more bouncing. Hey, when we talk about dispersion, it's all about optical wave, the speed of the optical wave inside the material. So we are talking about this light ray and this light ray propagate at different speed. But in the waveguide, we call the light ray can propagate inside the waveguide is the kind of mode, right? So this kind of dispersion is called modal dispersion. So this is another kind of dispersion, not quite material dispersion. It's called modal dispersion. Okay. So in the optical waveguide, in the optical fiber, we have this kind of material dispersion. We have also modal dispersion. When you have light going this, and when you have light going this, and you have modal dispersion. And in addition, there's other kind of dispersion, and I have more toy for you to see. This is a calcite crystal. This is a calcite crystal. What do you see? You can see nothing. This is a calcite crystal. If you put this onto a piece of fiber, a piece of paper with a thick line, somebody has a piece of paper with a thick line. It's either this one or but the line coming out is already polarized. Okay, good. You can see. But if I can see the, if you have a thick line, but this is not ideal because the light coming out from this screen is already polarized. Okay, but you can see that through this crystal you see two lines. Okay, you see two lines.
Yeah, I see.
And then.
You see anything else? No.
And you see two lines.
No.
You just no.
Maybe with.
Well, if you have a piece of paper. No, this one. This is perhaps this. Okay, if you can see clearly, then.
No.
It's this one, but that. And then use a polarizer. View through the polarizer. And then you can select the line you want to see. And when you select the line, the polarizer has to rotate exactly 90 degrees. For some reason, I'm missing polarizer. Oh, right here. This could be easier to see. Okay. Just view through, this is easier. This one, if it was it, you can select the line you want to see, and you're going to see that you have to change the direction by exactly 90 degrees to see the two lines clearly. What does it mean? It means that the refracted light going out with two different angles. That's why you see two lines. Okay, you see two lines, and then you tell that the two lines, the line associated with each line is the polarization dependent. The polarization of this line is perpendicular to the polarization of the other line. Okay, you can select the line you want to see. Well, after this class, I will still be here a little bit for you to play with it. Okay? So this means that the refractive index can be a function of polarization of the light. Okay, so we have another kind of expression called polarization dispersion. Because different polarization of the light will see different refractive index, so it's coming out with different angle by virtue of Snell's law. Okay, by virtue of Snell's law, if the refractive index is different, seen by the light, the axis angle will be different. That's why you see the line split into two lines. And then the light associated with each line is polarization dependent. So you can use a polarizer to select the line you want to see. And we call this polarization dispersion, because different polarizations of the light will see different refractive index and propagate at different speed. Okay. So in this optical fiber, there are three kinds of dispersions. Number one, material dispersion. Number two, modal dispersion. Number three, polarization dispersion. And that causes the signal to propagate at different speed. When you send this 0101 signal through the optical fiber, this is a pulse. Whenever you have a pulse in time, you need to add different frequency components into this. Okay. And in the end, the digital signal will turn out to be like this. And this is something you don't want. This is serious, right? You don't quite see the 0101 at your output anymore. So in the optical fiber, you have to manage dispersion. Otherwise, you cannot propagate this digital signal through this optical fiber. In the end, you see this, and this is sort of meaningless at your output. So this is a very quick concept about optical fiber, and this is from your textbook. All right, is there any question? So I'm very practical when I introduce this, but there are a lot of physics derivations in your textbook. Okay, you have to go through that by yourself. All right, any question? All right, then I want to talk about your eyes. What is the anatomy of your eyes? I'm too excited and I lost my pointer. Okay, anyway, your eye is an optical system consisting of two lenses right here. The one exposed to air is cornea, and then the second part is a crystalline lens. And this is doing the primary function of the image. And the beauty of your eyes is that your eyes of course look beautiful, and the beauty of this is that you have some muscle here to control the focal length of this guy. So, when you are young, like you can adapt to a lot of the situations by using your muscle to control this crystalline lens. But at my age, my muscle is not strong enough to control it. So I need to rely on glasses. Okay. So these two lenses basically form an image system for you to see something. Interesting. Okay. Now, when you're young, when I was young, I become nearsighted. People call this myopia or something, nearsighted. What happens is that in the regular eye, healthy eye, the object at the infinite is going to form a point image. It's going to form an image on the retina. Okay, but when you become nearsighted eye, then the image is going to be formed here in front of your sensor, before your sensor plane. And in the regular situation, for example, when I look into you with a healthy eye, well, previously when I have an object at the infinite, it's going to be here, but then I can still see you. The reason is that I can use my muscle in the eye to accommodate something that is closer than at infinite. Okay, and so for healthy eye, I'm going to have this kind of situation. In a regular case, I can have the image on this. Okay, but for nearsighted eye, without any accommodation. Well, by the way, using the muscle to adjust this is called accommodation. Okay, without accommodation for nearsighted eye, this point, the image plane is ahead of this retina, your optical sensors in your eye. Okay, and then at some far point, at some distant point, still the image cannot reach this. Okay, without any accommodation. Okay, and so only if you bring your object to be somewhere, some point that is not so far, then you see something. Okay, and if I want to restore my eye to a healthy eye, then I want to put a negative lens like this in front of this. So just mimic a healthy eye that can image something at infinite to the retina. So could you put this in front of this, like this, then the image start to form on your sensors, on your nerve. Okay, so this is how you correct the nearsighted eyes by using this negative lens. Okay, but then when I get old, the situation is different. This point is going to be behind the sensor, so I need to use another kind of positive lens to do the correction. Okay, but most of the time we're looking into something that is not at infinity, and so we still rely on this muscle to do the correction. For example, this object is not at infinity, but it can, after correction, it can still fall on this retina. That is because my muscle here still be able to sort of adjust the focal length of this crystalline lens, so that I can see something closer, not at infinity. Okay, so this is how people use negative lens to correct the nearsighted eyes, and so that you can sort of taking the good image in your daily life. Okay. Is there any question about this? So basically, the 2 points is that the number one, you have an optical system for doing image, and this is your sensor plane, your focal plane. Okay, and people call this the retina. Okay, and then there's a muscle here for you to do some adjustment, and we call this accommodation process. But if your eye sort of like my daughter, she spent too much time on the cell phone, and then start to get nearsighted, then she's now wearing this correction lens. Okay, so this is the sort of another thing relevant to your life. All right, aberration. The good thing is that today you saw aberration in your eyes. Okay, when you use a lens to do image like this, you see distorted image of this light. And then we're going to talk about different kind of aberrations. After we finish this part, then we're going to go into rigorous rematches to model the optical imaging in the system. Okay. So aberration, we have different kinds of aberration. Just like a dispersion, we have material dispersion, model dispersion, polarization dispersion, and so on. And for aberration, the first thing is that we have chromatic aberration, regardless of the surface of the optical element, because different colors of light is going to have different. Is going to see different refracting index. Okay, so you're going to see that if you have some perfect lens like this, okay, with perfect surface, you still see that different color of light will be focused to different point on the axis. We call this chromatic dispersion, and it's very hard to correct it. Okay, but there are ways to correct it. For this case, the blue light has a large bending because the refracting index is larger, so the bending angle from the Snell's law is larger. So you focus at this point. For red light, it's focused to this point. And then right here, we have the sort of spot of risk confusion. Okay, sigma LC is called the circle of risk confusion. Okay, so you're going to see a small spot here, not a single point in space. And this is so chromatic dispersion. But then if you use a negative lens, then the left focal plane will just reverse this kind of situation. Okay, the blue light is going to go in the opposite direction. Okay, because the refraction become reverse. Okay, so for correcting this chromatic dispersion, quite often people just use one positive lens and one negative lens to get a better focusing effect. So this is a very simple correction mechanism that you use the positive aberration, you use negative aberration to correct positive aberration. And we're going to come to this point later, okay? But just to let you know that you can play with the surface, the positive lens and negative lens to correct this chromatic aberration. Okay, and this is called doubly lens. Right? Well, because this is an engineering class, so I need to sort of telling you the rather useful applications. Okay, lens aberration, another kind of aberration is that if you use the chip lens, and in fact that is popular lens, you have spherical surface. When you have a spherical surface, then you understand that the non-paraxial light, the light going away from the center, is going to suffer from the spherical aberration, because spherical surface is not the right geometry for, say, focusing light into a spot. So you start to see that, well, this is a paraxial ray around this axis, and you have a focal point right here. So this is the usual focal point if you have a paraxial ray. But sometimes if you try to image something really big, then you have non-paraxial rays. It's going to focus to somewhere here. Okay, just like when we want to use this to image this monster, you have a lot of paraxial lights, and then you start to see that you have distortion away from the center of the axis, And this is what you just saw a while ago, right? In the last 1 hour. And so you have a paraxial ray focal point, and this is a of axis ray focal point, and the envelope of this is called caustic. Okay, so now we try to establish the language. This envelope is called caustic. Okay, and then we have longitudinal spherical aberration. Longitudinal spherical aberration is between the paraxial focus and the non-paraxial focus point. This point and this point is called LSA. That is longitudinal spherical aberration. Okay, so this is the language when we talk about this kind of aberration. And then, in contrast to this, we have transverse spherical aberration. That is this distance. Well, the distance is that from the axis to the between the intersecting point of a non-paraxial ray, right here, non-paraxial ray, with this focal plane. Then you measure the transverse distance. We call this the transverse spherical aberration. Okay, so this is distance between the intersecting point of a paraxial ray on the paraxial focal plane. This is a paraxial focal plane formed by the focal point of these two paraxial rays. So this is how we determine how serious the lens aberration is. Okay. And of course, the how serious it is depends on how much or how many non-paraxial rays you have in an imaging system. If you could keep everything near the axis, then the aberration can be reduced dramatically. Okay? But this is just one of several aberrations you can see from a spherical lens. We have more other things. Okay? We have other things, and well, we touch a little bit on positive aberration and then negative aberration. Okay, for positive aberration, well, the marginal ray of a positive lens are focused to point preceding the paraxial focal point, and that is what we just had right here. We call this positive aberration. Okay, this is non-paraxial ray that focus before this paraxial focal point. We call this positive aberration. But then if you have a negative lens, then you will have negative aberration. Okay, and so this is sort of conceptual illustration. So if you combine positive lens and negative lens to form a double lens, then you can reduce the aberration quite a bit. And your textbook, it shows you different kind of contact. Okay, but this is the by engineering. You can just appreciate it by reading through it. Okay, you can, for example, edge contact. You can have some cross-center contact, for example, and in the market you can buy different kind of double lens to reduce the aberration, even though this is a spherical surface. Okay. So spherical mirror, spherical lens have been very, very popular since the invention of it over decades. Still that people use spherical lenses quite well because people figure out how to reduce the aberration. Okay, now if we have a lens, like this is a plano convex lens, right? Plano convex lens. You want to use it like this, or you want to use it like this? Well, this is the sort of becoming the common sense. If you ever study optics, you want to choose this configuration. You want to have the convex side facing the incoming light. Okay, and one time I had a lunch with Steve Chu, who was a professor of Stanford a long time ago. He later became the Secretary of Department of Energy of the United States. Steve Chu is also the Nobel laureate due to his invention of the laser cooling. And then in the lunch with me, he told me that if a college student even know how to use a plano convex lens, this means that he or she already took the optics class. Okay, and what he talked about is exactly how this is going to reduce the aberration compared with this. Okay, for this one, you have more aberration than this one. Okay, and the reason is that that is the reason we talk about Riemann deviation angle. If you work with a lens close to this point, you see this is quite flat. This is quite flat. Okay, so this means that for whatever chromatic aberration or spherical aberration, if you operate near this point, it's not so sensitive to the entrance angle of the light. Well, see, for this off-axis light, you have large angle. Okay, for this paraxial light, you have smaller angle. Okay, so if you work at this point, the output is not going to be very sensitive to the input angle. Okay, and so if you compare this with this and also compare this with this, you notice that for this configuration, you have a entrance angle. But for this one, you don't have an entrance angle because this is just 90 degrees. But for this one, you have an entrance angle. That will move the point to somewhere closer to this. Okay. So with this, you have less aberration. So whenever next time, if you have a plano convex lens, you need to use this surface facing the incoming light. Beijing, next time, you guys will have a lot of experience in the graduate school, okay, when you do experiments. So this is sort of becoming common sense when you pick up a lens for your purpose. This kind of lens is very easy to fabricate. You just polish this side flat. That is very easy to do. And then just polish the second surface with a curvature. Okay. You don't need to use double convex lens for your purpose. Just use this and then use this side to face the light to come in. All right. So this is we're behind the schedule. Coma is another thing. Show up in the aberration. If you have some of, if you look into some off-axis image point, what happens is that the off-axis image point, if I want to image this point to the image plane, you found that for the light going through different part of the lens will be focused at different point. So it smear out the image, okay, and we call this coma. And I have some experiment. This experiment is quite easy to do. You just have a transparency, and then have different plots to transmit the light, and put it in front of the lens, and you're going to see that the different circles will be focused to different location on the image plane. Okay, and this is associated with the off-axis the image point. The best way to understand this is that And the best way to understand this is that on the image plane, even though you try to image this point to a single point on the image plane, but for the light ray going through different parts of the lens, it's going to focus at different location. Okay, and this is so called coma. Okay, and in your textbook and also in some office textbook, it analyze this for you. Okay, but visually you can see this by doing this very simple experiment. Okay, just put this mask onto your lens, and you see that, for example, this ring is going to be focused to this. And for the off-axis ring, supposedly it should go to a point, but in fact it's going like this. And overall, it's just like a comic, how they call it, the Huixing, like a shooting star kind of shape. Okay. So this is called coma. Additionally, we have other things. The coma, in fact, for this case, a simple way to reduce the coma is to use appropriate aperture. You can put aperture in front of this lens to reduce coma. Okay, and in this illustration from your textbook, if you have an aperture for the aperture sigma 1, the chip ray is going to be this one. Okay, and then these two rays is going to focus to the same point right here. Okay, but if you use different kind of aperture, for example, sigma 2 right here, sigma 2 is this aperture, then this is going to be your chip ray, and you see that this 2 will still focus to this point. But this ray, this off-axis ray, is going to go to this point. Okay, if you trace this beam to this point. So you have, for example, the positive, this is the positive coma, this is the negative coma, negative coma. Okay, but then if you use the aperture like a sigma 3, the chip ray becomes this. And this two will still focus to this point, but then this line is go to this point. So a different kind of aperture is going to give you a different kind of compensation for the coma. Okay, and the best one, of course, is to just use the aperture of sigma 1. Then this is symmetric. These two are symmetric. Therefore, all three rays will go to the single point. Okay, if you choose, for example, this aperture, and supposedly these three rays in parallel will focus to one point, but in fact they focus to 2 points here and here, and this the off-axis ray is going to give you a positive coma. Okay, so to remove coma, you can use the apertures in front of this lens. Try to limit the off-axis ray. So this is one way to reduce coma. Okay, and there are another kind of aberration we call astigmatism. Okay, and that is something I will continue on Wednesday, and I hope that I can move a little bit faster during the online class on this Wednesday. And so this is the 4th week. So this means that everybody should be serious about this class, because you're going to read more and more materials in the textbook and also handout. So make sure that you follow the schedule for the course materials. All right, and don't forget that you also need to turn in your first homework assignment next Monday. Okay. So I will see you online on Wednesday.
Are you going to Sweden or not?
Now I decided to stay with you guys.
Thank you.